Okay, this is the second half of worksheet 12.9, which was for response number 3. And so you should have tried these problems before. And you should be, this one's kind of a interesting twist. So let's see. So you got a table, but it's like got a bunch of positives and negatives in there for, I guess, intervals. And it has some values. It says let f be a function that is continuous from 0 to 4, not including 4. It's kind of interesting. Function f is twice differentiable. That means its first derivative exists everywhere and its second derivative exists everywhere except at x equals 2, which you'll notice first derivative D&E stands for does not exist. First and second derivatives don't exist at x equals 2, but they exist everywhere else. The function f and its derivatives have the properties indicated in the table above, where D&E indicates that the derivatives of f do not exist at x equals 2. For part A, for 0 to 4, find all the values of x at which f has a relative extremum. So that's relative maxes and mins, extremum. Determine whether f has a relative maximum or a relative minimum at each of these values. Justify your answer. How do you think you're going to justify relative maxes and mins? Most likely, first derivative test. Unless we can't, then probably second derivative test. So first, we need to figure out where the critical points are. And that's where f prime equals 0 or undefined. So there's two critical points at 1 and 2. And at 1, it's going from a positive slope increasing to a negative to another positive slope. So that's like a plateau. At the does not exist one, it's going from a positive slope to a negative slope. So that's a relative max. That's neither. So let's put that into words. I mean, everything we wrote on that table probably isn't going to help us. So we're going to say f has a critical point at x equals 1 since f prime of 1 equals 0. But f prime of x is positive on the interval directly to the left, which I'm going to call 0 to 1. And f prime of x is also positive on the interval directly to the right, 1 to 2. So f has no relative extrema at x equals 1. So I'm just putting my thoughts down that I looked at that one. F has a critical point at x equals 2 since f prime at 2 does not exist. Okay, so if you're going to justify relative max or min, you need to first state that you have a critical point. You might want to state why you know it's a critical point, which is what I've done. And f prime of x is positive on the interval directly to the left, 1 to 2, and f prime of x is negative on the interval directly to the right, 2 to 3, which means f has a relative extrema, and more specifically a relative maximum at x equals 2. Well, that's kind of the guts of it. Well, what's the name of the thing that we're using right here? Using the first derivative test for relative extrema. That's the full proper name for it. So I think that's a nice, I mean, identifying it, figuring out the answer is pretty easy. Now, justifying it, that's a little tougher. So, all right. Part B, on the axis provides sketch the graph function that has all the characteristics of f. So essentially, we're kind of working backwards from this information and trying to sketch a graph. Now, what I would do first is probably put the x-intercepts first, which are 0, x equals 1, and 3 has a 0 value. And then the first chunk is negative, so it's below the axis, but it's increasing up to 0. And the second derivative is negative, so it's concave down. So I'm going to say, and do they give us an initial condition or anything? Well, yeah, at x equals 0, this is negative 1. So we could put all these points on here. At x equals 2, the function is at 2. And at x equals 3, it's at 0. Okay. So I'd get all the points down that we know. And then then the first chunk is increasing but concave down. And then it gets to a 0 slope. So it should be a nice 0 slope here. And then it's increasing up to this point, but it's concave up, and then it hits a does not exist, but it's a continuous graph, so it's got to be kind of like a cusp or something, and then it's going down, but it's positive, going to a 0 slope at 3, and it's concave down, so that's why we're getting this cusp, because it goes from concave up to concave down right here at this sharp point. And then from 3 to 4, it's below the axis, it's going down, and it's concave up. And then I think we should put like a open dot here, because we don't really know information about 4, right? We don't actually know the value of 4. So something like that. Now, this is the only time I've ever seen this on any Fourier response problem in the 20, 30 years of Fourier response problems, like sketching the graph. So probably won't happen for you, but that's part B. Part C says let G be the function G equals the integral of f. Now, right when you see this, you should be like, oh, I know what's going to happen. G prime is going to equal f. So f is going to equal G prime. All right, have we seen that enough? Our function is defined as the integral of another function. We'll see what happens on open interval, 0 to 4. For 0 to 4, find all the values of x at which G has a relative extremum. Determine whether G has a relative max or relative min at these values, justify answer. So this is just like part A, but with a new function G. So I'm going to write that down. Gx equals 1 to x of ft dt. And so we need to find critical points, right? Well, we got to find the derivative then. And that's fundamental theorem of calculus part 2. You plug the derivative undoes the integral, and then you plug limits in. Then you got to multiply by the derivative of what you got plugged in. You got to plug the 1 in also, but the derivative of 1 is 0, so that drops out. So G prime of x equals f of x. And we want to figure out whether that's equal to 0 or undefined. Now we're going to do that by looking at the table and saying when is f equal to 0 undefined. So that happens at x equals, so these are your critical points. That happens at x equals 1 and 3. So let's see if we can describe what's going on. So we could say G, I'm going to kind of write it just like I did up there, but anytime I talk about G prime being positive or negative or zero, I'm going to always connect it back to F because that's the information they gave us in the table. So we got to kind of show them how we know what we know about G in relationship to the information they gave us for F. So G has a critical point at x equals 1. Now, by the way, so now F equals G prime, right? F equals G prime. So now G is decreasing. G is decreasing. G is increasing. G is increasing. And then G is decreasing. So I'd say there's a relative min there and a relative max right there. But now we just got to put it into words and justify it using the first derivative test. G has a critical point at x equals 1 since G prime of x, which equals f of x, or G prime at 1 equals f of 1 equals 0. And G prime of x, which equals f of x, is negative on the interval directly to the left, 0 to 1, and G prime of x, which equals f of x, is positive on the interval directly to the right, 1 to 2. So G has a relative extrema at x equals 1, and more specifically, G has a relative what would we say, minimum at x equals 1 using the first derivative test for relative extrema. So that's a really good answer. Justified, very specific. It's positive here, it's negative here. All right, but we also need to do G has a critical point at x equals 3, since G prime of 3 equals f of 3 equals 0, and G prime of x equals f of x is positive on the interval directly to the left, 2 to 3, and G prime of x equals f of x is negative on the interval directly to the right, 3 to 4. So G has a relative extrema at x equals 3, and more specifically, G has a relative maximum at x equals 3 using the first derivative test for relative extrema. It's a really good answer. I don't know if you need that every time to get all the credit, but that's a very safe, well-justified, very specific answer. D says for the function g defined in part C, find all the values of x on 0 to 4 at which the graph of g has a point of inflection. Justify your answer. So we're trying to find inflection points. Now, justifying your answer for inflection points, which comes from the second derivative, is not the second derivative test. That's for finding relative maxes and mins. Totally separate from finding inflection points. There's no name for the test for finding inflection points. It's just specifically inflection point is a place on a function where the concavity changes. So you just need to show that the concavity changes. Now, this is for g. So we need to find g double prime of x, which equals f prime of x. And we want to figure out where it equals 0 or undefined to find potential inflection points. These aren't for sure inflection points. So if you look up here, we're looking at the f prime line, which is g double prime, and it equals 0 at 1 and does not exist at 2. So it's 1 and 2 might be inflection points. Now we can tell right now it goes from, for g, this is concave up, this is concave up, so that's not an inflection point, and this is concave down from g, so that is an inflection point. So we got to put that in words. Gx has an inflection point at x equals 2 since g double prime of x, which equals f prime of x, is positive on the interval directly to the left, 1 to 2. So I'm always making connections back to f to show them I understand that. And g double prime of x, which equals f prime of x, is negative, concave down on the interval directly to the right, 2 to 3. So gx changes from concave up to concave down at x equals 2. That seems like a really good explanation, justification. There's no name. Don't say second derivative test when you're finding inflection points. So this problem is kind of interesting. It was kind of a weird table. It had all these words, positive, negative in it, so that was kind of weird at first. But here's the deal. There was very little work to be done. There was like almost no calculations, right? But there was a lot of explaining what we're doing. Things that were pretty quick to, find, to identify. Okay, let's try the last one. So, no calculator, considers a closed curve in the xy plane. So here's a curve, not written in very nice form that we're used to. She says, show the derivative equals this. Now, to take this derivative, to do it explicitly would be a lot of work, and I think probably impossible to get a single y by itself in terms of purely x's. But look at the answer they're giving you. It has y's in the derivative, which means you want to do this implicitly, which is going to be the easier way of doing it anyways. So part A is just saying take the derivative of this, find dy dx, and this is the answer, by the way, just in case you get something different. So make your answer look like that. So I'm going to rewrite the equation here, and we're going to take the derivative implicitly, which isn't that crazy of a thing. So we're taking derivative with respect to x. So this is going to be 2x plus 2 plus 4y cubed. And this is where you need the dy dx because y is a function of x. It's like an inner function. This is chain rule. but we're not going to actually find y in terms of x, so we just put a dy dx to represent its derivative, plus 4 dy dx equals 0. Now that's where the point right there, just having done that step correct. Now we got to get the dy dx's by themselves. So I'm going to factor the dy dx out of those two terms, 4y cubed plus 4, so I can get them together. I'm going to move the other stuff to the other side, minus 2x minus 2. Then we're going to divide both sides by 4y cubed plus 4. And that's our dy dx, but I think we want to try and simplify it. We want to make it look like that. So one of the things I noticed is I could take a 2 out of everything on the top and the bottom, right? That's simpler. Now I see this up here. It's like, well, I can make it look like that by factoring the negative out, right? Put in parentheses, and I can make the bottom look like that by factoring the 2 out. And we officially have dy dx equals negative parentheses x plus 1 over 2 parentheses y cubed plus 1. And we did it. All right. Part B says, write an equation for the line tangent to the curve at negative 2, 1. Now you need the slope to do that, but you could have totally skipped part A and just use the slope they give you, right? That's how we find the slope, is use dy dx. Now we need an x and a y value for this formula, right? Negative 2 for the x, positive 1 for the y. So it's going to be positive 1 over 4. So that's your slope. And so then our equation is going to be y minus 1 equals 1/4 x plus 2, and done. Don't do anything else to that. Just leave it like that. So you got 1 point for calculating the slope correct and 1 point for writing your answer. On this problem up here, you got 1 point for doing the implicit and 1 point for solving. So I think we've gotten 2 and 2 points. Okay. Part C says, find the coordinates of 2 points on the curve where the tangent line to the curve is vertical. Tangent is vertical. And we're trying to find the 2 points. So they're telling you there's 2 answers. So you shouldn't get 3, you should get 1, you should get 2. And the point should probably be x, y pairs, right? And say find the x coordinates, it said points. That means like the whole description of the point. How do we find when a tangent line is vertical? How do we find when a tangent line is horizontal? Horizontal tangent lines are flat, their slope is 0. Vertical tangent lines are straight up and down, their slope is infinitely steep, which is going to come when dy dx equals undefined, right? So we need to make the slope undefined, which is going to come from something divided by 0. So we're going to set the denominator equal to 0. Divide by 2, subtract 1, cube root of both sides. No plus or minus is an odd root. Y equals negative 1. Now, that's half of your answer because you need the x coordinate also. But something might also bother you that they said we're going to get 2 answers and this only gives us 1. Well, we'll check back in with that later. But how do we find the x coordinate that goes with this y value? I mean, since algebra 1, if I give you a y, could you give me the x? If I give you x, could you give me the y? Yeah. You're just going to use the original equation for x and y, their relationship with each other. If you plug negative 1 in for all the y's in here, you're going to get an equation that you can solve for x. So let's do that. It's worth a point just for plugging these things in. You got a point for finding y equals 1. So this is going to be x squared minus 2 plus 1 minus 4 equals 5. So it's going to be negative 6. It's going to be negative 5. So x squared equals 10. Wait, hold on. I think I made a mistake somewhere. Oh, plugged y equals negative 1 in for an x right there. So this should be x squared plus 2x plus 1 minus 4 equals 5. So this is a quadratic. So I think we want to move everything to one side. Negative 3 minus 8 equals 0. Factor it if possible. Otherwise, we're going to use quadratic formula. Pair of numbers that multiply together get negative 8. Add together get positive 2. It's going to be positive 4 and negative 2. And we get x equals negative 4 and x equals 2. Now, here's the interesting thing. That single y value gave us two different x values, which is possible. And those give you your 2 points. So one point's going to be negative 4, negative 1. The other point's going to be 2, negative 1. So the tangent line to the curve is vertical at negative 4, negative 1, and 2, negative 1. X first, y second. So that's a point, finding the final answer. So I think that's the 3 points. We're up to 7. So last one's got to be 2 points, right? So far, not too bad. Kind of a nice break from the last problem, where all we did was write tons of words. D, is it possible for this curve to have a horizontal tangent at points where it intersects the x-axis? It's asking you, can you have a horizontal tangent and an x-intercept at the same place? Explain your reasoning. So essentially, we're looking for horizontal tangents on the x-axis. X-intercepts. So how are we going to find this? Well, I don't know. There's two different things we've got to find. One idea is to find all the horizontal tangents, and another one is to find all the x-intercepts and see if any of them match up. It could be one strategy. Now, horizontal tangents, dy dx, has to equal 0. So we're going to take our dy dx equation that we found on part A, but they gave to us. So even if we didn't do part A, we could do this. And that has to equal 0 over a number. So then that means that negative x plus 1 has to equal 0. And so x plus 1 equals 0. So x equals negative 1 is a location of the horizontal tangent. That's a point for finding that. Okay. Now, the other thing is x-intercepts. How do you find x-intercepts? You set y equal to 0. So let's take the original equation, x squared plus 2x plus y to the fourth, plug 0 in for the y, plus 4y, plug 0 in for the y equals 5. And we get an equation, x squared plus 2x minus 5 equals 0. And if we solve it, that should give us our x-intercepts. Now, I don't think we can factor this, so I guess we're going to have to use quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You guys should know the quadratic formula inside and out. And that's going to give us negative 2 plus or minus the square root of 4 plus 20. And that's going to be negative 2 plus or minus the square root of 24. And then we could take the square root of 4 out of it just to simplify things. So we get negative 2 plus or minus 2 root 6 over 2. So we get negative 2 get negative 1 plus or minus the square root of 6. So we get the x-intercepts are at negative 1 plus root 6 and negative 1 minus root 6. And since these don't equal each other, then that must mean it's not possible. So we could say, no, the curve cannot have a horizontal tangent where it crosses the x-axis. Now, this is one way to do it. So you get a point for your final answer. Another way to do it is to here's something that would have been a little easier than this. I would have done this still, and then we say, well, this is where they have a horizontal tangent, and then we know that the x-axis, x-intercepts have to happen at y equals 0. So let's plug both of these in together and see if that point satisfies the original equation. Let's just plug them both into x squared plus 2x plus y to the fourth plus 4y equals 5 and see if it gives you a true result. If it doesn't, then that xy pair can't be on the line. If it does, then it is on the line. So we plug negative 1 in for x and 0 in for y. And we get positive 1 minus 2 plus 0 equals 5. So we get negative 1 equals 5, which is false, which means the point with x coordinate negative 1 and y equals 0 is not on this curve. So that's kind of a slick way. I mean, I feel like the way I did it was, to me, the most kind of like logical way to attack it. Find this, see if they agree. But this is kind of a little sneakier way of verifying that it doesn't happen. So that's it. I hope you're getting some good experience with this, seeing how the grading is broken down, seeing the kind of things that you should be writing in your work, justification. You need to be showing setups. You need to be very clear in your work to get all those points.